You're the first, right?
Yeah.
Okay. All right. Are we live?
We are live.
Okay, great. Well, welcome everyone to this cross-working group meeting on alternative Earths. And I'm very excited to see this great diversity of presentations that have been submitted. And I'm hoping for an exciting discussion after. And I think Betty and I thought that this would be a really nice session to have because we can see the use of CESM for non-traditional, let's say non-traditional, or at least pushing the model out of its normal comfort range, I would say, where we're asking to do things like run high CO2 atmospheres or changing the orbital dynamics. And there's been a great advancement, I think, over the last couple of years on making the model more transparent in terms of how you change things, and also that the move to GitHub and the idea that you can fork the model relatively easily, that now as I think maybe opened up the model to collaboration and co-development more. And so I think while this may not be what you could consider to be under NCAR's purview, model development, I think that the whole community is probably could benefit from maybe a bit of coordination in terms of co-development of these alternative Earth applications for the model. So looking forward to the session. And with that, I'll just turn it over to Betty, who's going to introduce the speakers and keep everyone on time. and then we'll have hopefully some discussion for the last half hour. Over to you, Betty.
So thanks everyone for being here. I'm really excited that there's so much interest, so many talks that were sent in to speak today. So we're going to spend about the first hour, or hour and a half, with 8 talks. And then we'll have a discussion, as Dan said, to just kind of think what we could do together, what should be done, how we can co-develop this effort, both for kind of early Earth and for other planets or other moons of planets. So I will be the person that keeps time. I will give you maybe a 2-minute warning before the end of your allotted time, just so you can think how to wrap up, what to finish with. We'll see if we have time for questions. My experience this week is it was often challenging, but questions can be put in the chat box, and we ask the speakers to look at that. The chat will also be saved. And then we, as Dan said, we may have a little bit of time also to discuss some of the science during our discussion section. One other thing is I'm pretty awful at pronouncing names. So if I mispronounce your name, please forgive me and feel free to correct me if I do poorly on your name. So our first speaker, an invited speaker, is Colin Goldblatt, and he's a professor at the University of Victoria. So Colin, I'll give you the floor.
Well, thanks everyone. It's a real pleasure to be opening this meeting. I'm just going to see if I can get this onto full screen first. That's great. Oh, we're not even on the first slide. So I'd like to present some work today, which is really my first experiment in using the Community Earth System model. So I'm very grateful to a couple of incredibly capable collaborators and co-authors. I've got Victoria McDonald, who was the student who did the model run, who's now at the University of Washington in grad school. She was a UVic undergrad then, and Kelly McCusker, who guided us through learning how to use the model, and she's at Rhodium Group. So we're going to talk about the problem of Earth's evolution and clouds. And the context for anyone not familiar with early Earth is the sun was less luminous early in Earth's history than it is now. So if we go back to the Neo-Archean, say 2.8 billion years ago, and that's the most that's the earliest time we've really got any constraint on the amount of CO2, or to be honest, anything in the atmosphere. And we'd need a radiative forcing of about 50 watts per square meter to keep the Earth warm in the with the sun being dimmer at the time. Now that would need about 100,000 parts per million of CO2. We're just using CO2, but that's more than the geochemical constraints indicate that we're allowed. So a little bit more background. Here's an artist's impression, I'm going to call it, of the evolution of Earth's atmosphere. Some key things to point out is oxygen, we do know the history of. It's really reactive. It leaves a great geochemical record. That rose from part per million to percent levels around 2.5 billion years ago. Our other major constituent, nitrogen, we have very little constraint on the history of it. It was probably about what it is now, to within a factor of 2 or 3, probably. Water is, of course, determined physically, and CO2 is determined by, to a large extent, the carbonate silicate weathering cycle. So that probably decreased over time. So here's some super old results, or 10 years old, from 1D modeling. So this is what I was doing before I learned to run the community Earth system model. And we're going to, in this figure, I changed shortwave, I changed low clouds on the bottom row, middle clouds on the middle, and high clouds on the top. And we've got the shortwave, long wave, and net forcing. So you can see, if we just look at the bottom row for the moment, that at the moment, low clouds give us about a 30 watts per square meter negative forcing. So if we took low clouds out, that could give us a lot of the forcing that we need to resolve the faint young sun. Equally, if we go up to the top row and the middle, we can see we get, some forcing from high clouds. And if we were to increase the amount of high clouds, we could, again, contribute to the faint young sun. And we're going to focus here in this talk on the low clouds. So here are some low clouds, and we're going to be talking about, marine strata, stratocumulus. These are, just hanging out in the boundary layer. So not very high, don't have much of a greenhouse effect, but they really are very reflective. So they're good at reflecting sunlight away. So if we had less of this type of cloud, would that make a contribution to keeping early Earth warm despite the dimmer sun? Let's look a little bit at the physics of them. These clouds form up, in the descending limb of the Hadley cell. You've got warm, dry air descending aloft, and then you've got a cooler ocean surface, shallow convection, and they're also in the, quite near to the equator, these belts of clouds. That's actually where it is sunny, Up here in the north, it doesn't really matter how much cloud we've got, because there's not much sunlight to reflect, except today in Victoria. It's a beautiful sunny day here in paradise. So this again is the physics that we're looking at. So it's these clouds here that we're going to be seeing whether we can get rid of some of. And just one more schematic about the physics here. These form up below the inversion, and a stronger inversion is really good for these clouds because it prevents the entrainment of dry air from the free troposphere into the boundary layer, which would dry out the cloud. And the shallow convection is driven by cloud top radiative cooling. So we can think about that. Maybe if we had more CO2, we'd inhibit that cloud top radiative cooling, and that would be bad for the clouds. We wouldn't drive that convection as well, that shallow convection. Then one more schematic. This is out of a Brotherton paper, I think. There's a couple of metrics that are used to measure the strength of the inversion at the planetary boundary layer. One is the lower tropospheric stability, and that's the temperature difference, the potential temperature difference between the surface and 700 hectopascals. And the other is the estimated inversion strength, which is a difference in wet bulb potential temperature between the lifting condensation level and the free troposphere. You could measure that at 700 hectopascals. So the LTS is a slightly older metric. The EIS is the more refined metric. So now let's get on to some modeling here. We were interested in atmospheric processes and, had somewhat limited computer time. So we were running with a slab ocean. And we really wanted to do a very controlled experiment here. So all we changed was CO2 and solar constant. And we changed them pairwise such that we got the same mean surface temperature. So we're trying to use the model in a place where we can really trust that the model should be working well. At a mean surface temperature of 288, 289 Kelvin, the model really should work. So we turn down the solar constant and turn up CO2 just until it's balanced. And we did this both in CAM 4 and CAM 5. We were successful in getting CAM 4 to run as low as 0.7 and as high as 1.1 solar constant relative to the modern. And we did runs with CAM 5 in a narrower range where we could successfully get the model to work. So this is a controlled experiment. One of the things to emphasize is a lot of the critical parameterizations change between CAM 4 and CAM 5. The boundary layer, some of the cloud parameterizations, especially for low cloud, the radiation as well. So some of the things that really matter are different between these two model versions. And we did check on the radiation scheme, and CO2 is moderately well behaved up to about 30,000 ppm in the out-of-the-box model, maybe even a little higher. You might not want to trust the high CO2s as simulations of what happened, but as a controlled experiment that's internally consistent, I'm pretty happy with it. So I'm going to show you a bunch of figures that look like this. And on the left-hand panel, we have the modern case. And on the middle panel, we have the 0.8 solar constant case. And on the right-hand side, we have a difference. And this is for 0.8 solar constant with CAM 4. So we're just looking at a couple of bits of model climatology. Surface temperature, you can actually see a difference without looking at the difference field. You've got warmer poles, slightly cooler equator, but the same mean surface temperature. And that's, of course, because we've got a stronger greenhouse that's good at keeping the poles warm, but weaker solar constant, so that's heating the equator less. And then latent heat flux, we're seeing less latent heat flux. That's because we're warming up the equatorial ocean less. And then let's go on to these stability metrics, which are telling us about how strong our boundary layer is. And we see globally much weaker lower tropospheric stability, much weaker estimated inversion strength. And if it's projecting well enough on zoom in these stratocumulus regions, so here off California, here off Peru, off Namibia, you can actually see the biggest differences are in the stratocumulus regions. So that's quite exciting about getting some potentially interesting results. So here's a little bit more of the climatology. Here are some zonal means. We can see those big differences in the equator to pole temperature gradient again. And then, what else would I want to draw your attention to? Some of the temperature structure here, and also some of the drying of the equatorial atmosphere here, and a little drying of the free troposphere in the subtropics and mid-latitudes. Okay, so let's go on to our low cloud changes. And, again, this is just, we were so excited when we saw this result because it's something that you can see without plotting up the difference field, which is for something where we're looking at early Earth, that's just so great because it's such a strong signal. We might actually trust it. You can see that we've annihilated our low clouds. The difference between modern here and 0.8 solar constant in the different field. Again, you know, the browns are much less low cloud fraction. And we see these really big difference in the stratocumulus region. And then if we look at cloud water path, the middle row here, again, we see a loss of cloud water path everywhere. And that gives a positive forcing. We're reflecting less sunlight. And that is very clear globally, but again, especially in the stratocumulus regions. So that was a super exciting result to see. And this is looking for a time slice from 0.7 solar constant at the bottom right to 1.1 at the top left. And we see this just really well-behaved signal throughout our transect of solar constant CO2 space. So again, super exciting, super clear result, which is really the kind of thing we want to see in deep paleoclimate. I'm going to talk very briefly about high clouds. We do actually see more high cloud, but those high clouds are thinner. So overall, those two effects seem to cancel out. So there's not much difference in the long wave cloud forcing that we, you know, is dominated by those high clouds. And again, if we look at that transect, we really don't see much difference in the high clouds. So this is everything altogether. If we look at the top left plot, this is how much CO2 we needed to maintain the same surface temperature. And if you can see on zoom, the gray line, it's about a factor of 3 less than we'd expect if we'd run a 1D model with fixed clouds. And to give credit to the prior art, I think we'd seen results like this in some of Eric Wolf's work from a few years ago. So that wasn't entirely a surprise, but let's really get at these systematic changes to clouds. So if we go to the bottom panels, on the left, we've got this really systematic change in low cloud fraction, the bottom middle, change in low cloud water path in these dark blue lines. And then bottom right, we see the really strong change in the red line of shortwave cloud forcing. That's less reflection due to less low cloud in the past.
2 minutes, Colin.
Thank you. And then, you know, the physics driving this is a lot of it is this difference in the inversion strength. So we've got a stronger greenhouse, so the clouds can't cool as well. So that drives the shallow convection less. And we've got this weaker inversion. So it's easier to get exchange with the free troposphere. And that's really important in drying these clouds out and killing them off early in Earth history. So on time, here are my conclusions. I think I've told you about the first few. So some of my musings here is with this smaller equator to pole temperature gradient quite systematically, that's going to help protect us from glaciation. That's a big deal. The equitable climate means that if you move bits of weatherable land around in early Earth, we might be less susceptible to changes in weathering due to that relative to, for example, the Cenozoic. I've got a student, Keegan Gemmill, working on that right now. And the clouds are all going to really depend on the base climate state. So how much CO2 do we have? You know, what solar constant do we have? On all these planets that we're going to be exploring in this session today, we're going to expect clouds to look very different. So I think there's going to be some really fun work looking at cloud climatology on our diversity of planets. Thank you.
Perfect. So thank you. Fascinating. So I think we should move on so we have plenty of time for discussion, but please put some questions for Colin in the chat and Colin, if you could kind of keep an eye on that, and then we can also come back to discussions or questions during our discussion. So the next speaker is Professor Shields, a professor of the University of California in Irvine. You pronounce it for me and introduce yourself.
Yes, Omawa. Hi, everybody. Okay, let me go ahead and share my screen. Okay, hopefully you're all seeing that. I'm excited to be here today. I want to thank the organizers for the invitation to share with you some of the ways that my group has been using CESM to explore the possible climates of planets orbiting stars other than the sun. And I want to make sure to thank CC Bitts, my PhD co-advisor, who long ago introduced an astronomer by training to the capabilities of CESM as a powerful tool for this work. Our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars in a universe of hundreds of billions of galaxies. And as of yesterday, the current count of planets orbiting stars beyond the sun, which we call extrasolar planets or exoplanets, is close to 4,500. And this is across a range of different planetary regimes. And the ones that I'm most interested in are those that are close in size to the Earth, where they have the potential to be rocky, perhaps with oceans on their surfaces. Of course, the only planet that we absolutely know of where life exists is the Earth. However, we now have a growing number of planets that may possess the conditions amenable to surface liquid water, which we know all life on Earth needs and is sort of our criterion, our major criterion for surface habitability as we look beyond the solar system for where else life might exist. And among the most exciting prospects include several planets orbiting the star, the ultra-cool star, TRAPPIST-1, Proxima Centauri b, the nearest potentially habitable planet to us, LHS 1140b, for which we have both mass and radius information, allowing us to constrain its density as rocky, so then making the possibility of oceans more likely. And we know of this large number of exoplanets, largely due to NASA's Kepler mission, which stared at a particular patch of the sky and took snapshots looking for planets that transited in front of their stars from our vantage point here on Earth. Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS, is likely going to dwarf this number because TESS is an all-sky survey. And in the last 3 years, we already have several planets discovered in the Earth-size regime. And there, a few of them are to scale, with Earth and Mars to scale. And even more recently, we have a new planet, TOI 700d, very nice romantic name, which is the first Earth-sized planet found by TESS in the habitable zone, which I'll talk about briefly shortly. And TESS is looking at the brightest stars in the solar neighborhood. There are 30 to 100 times brighter than those sampled by Kepler. And that's great because that means these planets are going to be able to be followed up by next generation space-based missions. A few of them are shown here, both missions that are upcoming and current mission concepts, which we hope will eventually fly, in concert with dedicated efforts on the ground by extremely large telescopes. That is a technical term, ELTs. So that dual-based approach of space and ground-based imaging and spectroscopy is hopefully going to allow us to actually determine whether these planets in fact could host life and do host life. So we're entering an era where we have a quality problem. We aren't going to have infinite telescope time to follow up on every single potentially habitable world to look for signs of life. So we'll need a way to prioritize those planets to follow up on. And that's where the field of exoplanet climatology enters in. Historically, what observers do is find planets that orbit their stars in a particular region in space around the star, which we call the habitable zone. Too close in, the planet is in danger of losing its entire water inventory to space in a runaway greenhouse state. That's what we think the fate of Venus was. Too far away, and the maximum CO2 greenhouse limit is reached, that point beyond which you can't continue to increase CO2 and keep warming temperatures, to keep temperatures warm enough for surface liquid water. But we only have to look at our own Earth as an example of the fact that there are many factors and capabilities, many factors and processes that affect planetary habitability beyond orbital distance. Our planet likely experienced snowball episodes several times in its history while it lay very comfortably in its host star habitable zone. So the long-term presence of surface liquid water is influenced by a number of different factors, including stellar effects, planetary system effects and properties. The list is quite complicated. And my team has been slowly chipping away at this list for several years now, with a particular focus on surface composition. So how the incoming stellar radiation, which I'm going to call installation for the remainder of this talk, interacts with the planet's atmosphere and surface, and how that interaction can influence planetary climate and habitability. Because there are many surface types possible on a planet beyond ocean, including land and salty ice and salt-free ice, and the Ice-albedo feedback mechanism, which we know of as a positive feedback on our planet, could act very differently on the surfaces of other planets. So surface composition matters in climate and habitability studies, and that's one of my main points that I want to leave you with. And we've discovered that largely through the use of CESM. So let's talk about starlight. I'm showing you here the spectra of several different stars. Hopefully you can see my cursor here. The sun is shown in yellow, and we've got a star a little cooler than the sun, which we call a K dwarf. So the sun is a G dwarf, K dwarf here in orange, and a star a little brighter than the sun, an F dwarf in blue. You can see that the cooler stars, their peak flux is a little bit towards the longer range, and then the hotter and brighter the star, the more their peak flux skews towards the shorter end of the spectrum. And here over here is the red or M dwarf stars, whose peak flux is in the near infrared. So much longer wavelength compared to the sun. And this has implications when we talk about the Ice-albedo feedback mechanism. So quickly, we've used largely CAM4, or in later studies, ExoCam, which is based on CAM4, which our own Eric Wolf will be talking about later in this session. To change the host star spectrum, what we do is go into SourceMA's SRC CAM, and we can actually change the percentage of the flux in the different wave bands, their input to CAM. And that's how we can change the host star from the sun to a different star, a different type of star. So Ice-albedo feedback, we think of ice on our planet as being very bright white surface. The more light that ice reflects, the colder the planet gets, more ice forms, temperatures get colder, etc. It's a positive feedback process. However, Ice-albedo has a spectral dependence. So the Ice-albedo feedback mechanism is going to be sensitive to the wavelength of light coming from the host star. Ice absorbs longer, redder wavelength light and reflects shorter, bluer light. And so one of the first applications of CESM that I've ever been involved in to study exoplanets has been to look at this phenomenon, really looking at a planet's climate stability and how it was affected by this star surface and atmosphere interaction. So how it affected a planet's susceptibility to snowball episodes and how planets could thaw out of them. We assumed in most studies a slab ocean, and we used the sea ice albedo parameterization of the ancient CESM or CCSM3 because it's much more easily manipulating. You can easily manipulate it. So it's a two-band albedo parameterization where you split it at 0.7 microns for visible and IR. And if we look at M dwarf, G dwarf, and F dwarf planets, what we did was created these hysteresis curves. And the M dwarf planet had a smaller climate hysteresis. So in layperson's terms, it's harder to freeze, it's easier to thaw. And when it thawed with a shorter jump in ice line latitude, where the hotter and brighter the star, the greater the jump in ice line, and potentially making M dwarf planets better abodes for life. And the reason for this is twofold. We found that the ice albedo, which was lower on the M dwarf planets because those surfaces are receiving more near IR radiation, which the ice absorbs more strongly. That results in higher temperatures at those polar latitudes where there was ice on the surface. We also found, when we looked at the meridional stream function, a squatter and weaker Hadley cell on the M dwarf planet. So CO2 and water vapor, which are present in all planets' atmospheres, absorb more strongly in the near IR. And so we have a lot of short wave absorption happening in the troposphere, and that reduces short wave reaching the surface that's needed to drive convection. And we ended up seeing that more heat's retained in the tropics, less distributed to higher latitudes, and that aids M dwarf planets in thawing more easily out of global ice cover. And in later work with Eric Wolf and others, we were able to see this trend of solar stellar driven glaciation being more effective for planets orbiting redder stars across a range of climate regimes, from snowball through moist greenhouse. So to change the ice and snow two-band albedos, we use the sea ice or CEIS name list, and we're able to change the IR and visible albedos for both ice and snow. The spectral wavelength dependence is already present by default in sea ice or CEIS, but that's weighted by the suns, the solar spectrum. And so outside of CESM, I have a code that weights the two-band albedos by the particular spectrum of the host star. Then I just change those albedos in the name list file here. More recently, we've done trend birth diagrams for exoplanets. And this is the first time that this has ever been done because we knew that an M dwarf planet is warmer than a planet orbiting a hotter, brighter star, ironically, at an equivalent stellar flux distance. We knew this was because of this ice albedo effect, as well as increased atmospheric absorption on M dwarf planets, but we didn't actually know the specifics of how this was occurring. So how the energy budgets were different between these planets. And that was important to quantify. So what we did was carry out a range of simulations for F dwarf, G dwarf, and M dwarf planets, and calculated the percentages. So how the energy, the downwelling radiation from each star was distributed, was budgeted throughout the planet's atmosphere and surface and back out again. And for example, looking at the F dwarf planet, much more radiation, incoming radiation, is reflected by the atmosphere and the surface compared to the M dwarf planet. And so we have this table in this paper, Energy Budgets of Terrestrial Exoplanets, that contains all of these percentages for different host star types.
1 minute.
Thank you. We've also looked at non-characteristic surface types like hydrohalite, which can precipitate and bear sea ice at low temperatures, and created our own albedo parameterizations for the formation of that surface type in our GCM studies. And so hydrohalite, as you can see, is quite reflective compared to salt-free water ice. And this we discovered has implications for M dwarf planets. And so we were able to create our own, just add a few lines of text into the ICE shortwave file that allows for this albedo parameterization. And when we do that, we see quite a difference here. We're looking at the control case subtracted from having an albedo parameterization for hydrohalite, and we see quite a difference, especially, or even for planets that are in the habitable zone of their stars. So what this means is that an accurate assessment of surface temperatures for exoplanets requires parameterizations for this surface type into GCM studies. And we see this even stronger, this climate sensitivity, if the planet is synchronously rotating, where it's got the same side facing the star at all times. It's always daytime, and on the other side, it's always night. And we can do that in CESM by changing the orbital parameters, the rotation rate, and these source mods, SRC share and SRC cam directories. And I'm happy to talk more about these modifications separately with anyone who'd like to start running their own simulations of exoplanet climates. So I'm gonna stop there. We've done some studies with land as well, both with Eric and Marisa, who's here as well. And this work was spearheaded by my postdoc, Andrew Rushby. And we're able to actually use CLM to look at the effects of different land surface types on TRAPPIST-1 planets. And the short end of the take-home point there is that it matters. The difference is 50 Kelvin across the lowest and highest albedo land surface types. And it affects cross-equatorial energy transport, where we end up seeing much higher surface temperatures on the planets with the lowest albedo surface type, both due to atmosphere and surface effects, making TRAPPIST-1D the most likely candidate for habitable conditions in this system. So the takeaway points that CCSM is an important model suite used for exoplanet climatology. For the most part, we tend to keep our intrinsic parameters similar to Earth radius, Earth mass, surface gravity, and we change what we can without really going too far into the hard coding there. And it's helped us to highlight a very powerful effect on climate, which is this effect of stellar spectrum and surface composition. So to see more about our work, please visit our publications page. And thank you to my funding sources and all the collaborators of all the work that we've done over the past decade or so. And I'll take any questions. Thank you.
Well, thank you. And yeah, I'm going to go to the publication site. I know that, start reading. So we should move on, but I already see one question or two maybe in the chat. And so thank you. And we'll move on to our next talk. Greg Cook, who's a PhD student at the University of Leeds.
Hey, everyone. Let me just share my screen. So I think you can see presenter view, right? Yeah, okay. So you can see the main PowerPoint with the arrow. Okay, so yes, hello everyone and good evening from the UK. I'm very, very pleased to be able to give this talk. It's a great opportunity to present and discuss some of the work I've been leading. My talk is titled Viewing the Earth and its Exoplanet Analogues Through Time. So essentially we use WACM for paleoclimate studies and applied the results to exoplanets. So yes, I'd like to thank my fellow collaborators listed here, whose hard work has helped contribute to this talk. To give a brief overview, I'll discuss the oxygenation history of the Earth, then the simulations that we've done with WACM 6, before moving on to the results and implications, which is new ozone column predictions, new methane predictions, and the implications of changing oxygenation for exoplanets. So let's dive right in. This figure is from the Lyons et al. 2014 paper, and it shows the estimated oxygenation history of Earth for the past 4 billion years. We know that life has been present in at least 3 geological eons, the Archean, the Proterozoic, and the Phanerozoic. And oxygen was very low during the Archean, but then we had the Great Oxidation Event about 2.4 billion years ago, and oxygen rose to near modern levels. But then we had this dip for quite a long time where oxygen levels were between 10 to the -4 and 10 to the -1 the present atmospheric level before rising again during the Neoproterozoic oxidation event. And then during the Phanerozoic, levels have remained relatively constant, although they have fluctuated. So by extension, we can think that terrestrial exoplanets, rocky planets around other stars, will also go through geological evolution, just like the solar system terrestrial planets have. So the motivation behind our simulations is to better understand Earth's history and the potential state of the terrestrial exoplanets that we may characterize in the future. So what did we do? Well, we used the Wacom 6 configuration of CESM2, so that's the high top version of CAM6, to find out how changing oxygen concentrations affects Earth's atmosphere. So we performed simulations where the only variable change was the oxygen concentration. Several other species were held at a constant mixing ratio at the surface, but here we've just changed oxygen. So we start with the pre-industrial atmosphere, where oxygen is 21% by volume at the surface, but this decreases at the mesopause. And then we change oxygen to the values shown here, which is 150% the present atmospheric level, a possible high during Earth's history, all the way down to 1,000 or 0.1% the present atmospheric level. But we really wanted to sort of better simulate Proterozoic conditions too, after the rise in oxygen. So we have variations on the 1% PL simulation. We have two methane flux simulations where instead of fixing the lower boundary, we had a flux. We had two simulations where we had a 2 billion year younger sun. And then one of those simulations had 4 times the amount of pre-industrial CO2 to buffer that fainter sun. So each of these simulations was run out until roughly interannual equilibrium was reached for the last 8 years of the simulation. And then I'm going to present time average means for the last 4 years of each simulation. So here we have the oxygen, ozone, and temperature profiles on the x-axis with atmospheric pressure on the y-axis. The oxygen profile here with all the colors note from black and then into grey to go to 150%, then the greens 50 to 5, and the blues 1 to 0.1%, the present atmospheric level of O2. So yeah, this oxygen profile basically affects the ozone profile because oxygen has a large influence on the production of ozone, with oxygen photolysis being the main source of odd oxygen. And then as ozone absorbs ultraviolet radiation and heats the stratosphere, we see that as oxygen and thus ozone reduces, we actually have a much colder stratosphere. And essentially, when we get to 1% the present atmospheric level, the stratosphere basically disappears. And this is good news because it's been seen in previous 1D modeling. So the lack of ozone and oxygen allows increased UV to reach lower in the atmosphere, all the way to the surface. And this results in increased photolysis of important greenhouse gases, such as water vapor, methane, carbon dioxide, and nitrous oxide. So methane in particular is rapidly destroyed, first at the surface because of increased OH, and then in the just above the tropopause because of increased photolysis. As oxygen and ozone reduce, the water vapor content entering the stratosphere is much lower because of a colder tropopause. So this middle atmospheric loss of greenhouse gases is really important, and it has implications for detecting these molecules in exoplanet atmospheres, particularly in transits, as I will show later. So how protective are the ozone states that we predict? Here we have the total ozone column plotted on Earth for each oxygen case. The ozone column is simply the total number of ozone molecules above our heads per unit area. Note the difference in the scales. So we have a peak of 375 Dobson units in the pre-industrial atmosphere, and that goes all the way down to a peak of 24 Dobson units in the 0.1% PAL atmosphere. So in this pre-industrial case, we can see that the minimum ozone column is actually found across the equator as the Brewer-Dobson circulations distributes ozone to high latitudes. But this changes as oxygen is reduced, and essentially the distribution is no longer the same. We don't have quite the whole equatorial minimum across this whole band here. That breaks down. And there is no longer this distribution of ozone to high latitudes. And also notice that the magnitude of ozone does change quite drastically as we reduce oxygen. But how does this compare with previous work? Well, this plot shows how the O2 concentration varies with the ozone column it produces. So as oxygen increases, the ozone column generally increases, including for most previous work too. So the previous work is generally 1D modeling, apart from we have one 3D model here, which is the Webb 2017 Rocky 3D model from their work, and that's this dotted line here. So basically, we predict lower ozone levels compared to previous research. Biological and astrobiological research has generally accepted that when we get to 1% of present atmospheric level of O2, we have a substantial ozone layer which is able to shield the life and the biosphere from UV radiation. And this is indicated by this orange shaded box here. However, our results suggest that this assumption is problematic for both Earth's historical habitability and for exoplanet habitability. And this is because we need between 5 and 10 times the amount of oxygen to get to the same UV protective state as estimated by previous research with the amount of ozone that is needed. So we think that the UV levels in the literature may have been underestimated for much of the past 2.4 billion years, and that could have implications for complex animal life, particularly when the ozone layer is significantly perturbed by volcanic eruptions or flares. So if previous results have overestimated the protection from the ozone layer, perhaps ozone's influence on Earth's biological history needs to be re-examined. So moving on now to the Proterozoic faint young sun paradox.
Greg, 2 minutes.
I
2
thought
minutes.
I had 15 minutes.
No, you have 10 minutes.
Oh, okay. So between 1.8 billion years ago and 0.8 billion years ago, there's no evidence of widespread glaciation, but the sun was between 13% and 6% fainter, as Colin discussed earlier. So how is this possible? Well, previous research has invoked high methane and carbon dioxide to warm the Earth under a fainter sun. But is increased methane during the Mesoproterozoic possible? Well, we don't think so. Recent research has estimated that during the Proterozoic, methane fluxes might have been a lot lower than present day, perhaps even lower than 10% of the pre-industrial emissions. And here we have a figure that shows the methane mixing ratio and lifetime at these fluxes. So the lifetime is substantially reduced here. And then at the fluxes, we also see that the methane mixing ratio is really, really reduced down to very small values. So the Proterozoic faint young sun paradox does, in this sense, remain very much alive, and these results make it more difficult to solve. I'll just quickly skip ahead to some transmission spectra results. So as oxygen reduces, we have less ozone, and this basically means that all the molecules across the board here indicated from 0.1 microns to 20 microns are reduced in terms of their effective altitude, which is their relative light absorption, and this makes it much more difficult to detect them in exoplanet atmospheres. So yeah, if we focus on this ozone feature here, and we go and look at the next generation telescope LoveWire, which has been proposed, and we place a planet 30 parsecs away, we do 25 transits, then we find that we can detect ozone in the pre-industrial atmosphere, but not in the 1% PAL atmosphere, and we need a much, much bigger telescope, maybe even 100 meters in diameter, or we might need to observe for many, many more years. So I'll just skip to future work. So observational predictions and recommendations for next generation telescopes, that's what we want to do with all this work, not just LoveWire, but the European Extremely Large Telescope and some of the other ELTs. And we also want to make WACOM 6 much more flexible, and this will involve big jobs like modifying the chemistry and radiative transfer in the model. So yeah, I have skipped some things out there, but if you'd like to see extra details of the work, then we have an archive preprint, which is due to be updated. Otherwise, yeah, send me a question in the chat or send me an email. Thank you very much.
Oh, thank you, Greg. So again, put your questions in the chat, and we'll move on here to the next talk, which is Yun Yang, assistant professor at Peking University.
Okay, so I need to share my screen?
Yes, and I'll give you a 2-minute warning, so 8 minutes into your talk.
Okay. Sorry, it's deep night in China. I just get up just 1 minute ago. Okay. Could you hear me and see the screen?
Yes, all good.
Okay. Hi everyone. I'm Jun Yang from Peking University. Today I will show using CAM System 3 CESM for exoplanet climate simulations. First, I will focus on planets around M stars. These two panels show the habitable zone of G star and M star. Because the mass of M star is much lower than G star and the temperature of M star is much lower. So the habitable zone of M star is much more close to the host star. So planets in the habitable zone of M star will have much more higher tide force. So the tide force can push the system in tidal lock orbits, such as 1-to-1 tidal lock orbits. It means that the rotation period is equal to the orbit period. So the day side is permanent, and also the night side is also permanent. So only one hemisphere of the planet can receive standard energy from the host star. For simulation, the climate of tidal lock rocky planets, the process is similar to climate simulation of Earth, Venus, or Mars, but for different atmosphere mass, atmosphere compositions, clouds, convections, ocean depths, and so on. Many of these facts are easy to be modified in NCAP models such as CAM or CCSM, but also there are some parameters are very difficult, such as atmosphere composition, cloud, and convection. This is one example of the simulator surface temperature of a tidal lock rocky planet. As you can see that on the day side is warm, and the spatial pattern of the surface temperature is similar to the standard flux distribution. On the night side is cold, and the surface temperature is nearly uniform because there is no standard flux on that side, and meanwhile the rotation rate of tidal lock planets is always much lower than Earth. There is atmospheric heat transport from the day side to the night side. From the sea surface temperature, from the surface air temperature, we can know that because the day side is warm than the night side, so the surface air pressure on the day side is lower than that on the night side. So this surface air pressure contrast can driven strong convergence from the night side to the day side. And meanwhile, because the subsoil region is warm, so it can promote strong convection. So the atmosphere circulation is that over the subsoil region, there is strong convergence and convection. So clouds can form over the subsoil region. When the air flow close to the troposphere, they flow to the night side or the polar region of the day side, and then downwelling on the night side, and flow back to the subsoil region near the surface. Because the clouds are right at the region where the stellar flux is the maximum, so the clouds can effectively cool the surface and stabilize the climate. This cloud pattern have already been simulated by many GCM, AGCM. So all these simulations support that on tidal lock planets, the subsoil region should be covered by orbit sync clouds. But because different models use different cloud schemes and different convection schemes, so the simulated cloud water path and cloud fraction have large difference between different models. Besides the effect of clouds, ocean can also influence the climate. This pattern shows the surface air temperature and the ocean surface currents. As you can see that the hotspot is not at the subsoil region, the center of the panel, but on the east, the south, or the north of the subsoil region. This is due to that in the ocean, there are Rossby wave and Kelvin waves. The Rossby wave transport heat to the west and the polar region of the subsoil point, and the Kelvin wave transport heat to the east of the subsoil region. So the spatial pattern is like a monzonal gear mode. The waves also transport heat from the subsoil region to the night side. So actually, on the night side, the surface temperature is much higher than that in AGCM. Meanwhile, because the ocean can transport heat from the subsoil region to the night side, the ice only several meters or tens of meters. This thickness is close to the thickness of sea ice in the polar region of our Earth. So the ocean heat transport limit the growth of the sea ice to much sink. Besides of the waves, there are also strong currents in the deep tropical region of tidal planets. We call it oceanic superrotation because the ocean currents is from west to east and it can reach several meters. So it actually rotates faster than the solid Earth, a solid planet part of the planet. So it can be called oceanic superrotation. In both CESM3 and CESM, we can find a strong current in the equator region. The mechanism of this oceanic superrotation is through Rossby wave, which transport moment from polar region to the deep tropical region. Besides of the ocean, sea ice drift.
Did you hear 2 minutes?
Okay. Besides of the ocean, sea ice drift can also influence the climate. In this slide, I want to show how sea ice drift influence the climate of tidal planets. We want to know how sea ice drift can push the system from an eyeball-like state to a snowball-like state. And this video shows the results. The left panel is for without sea ice drift, and the right panel is for with sea ice drift. You can see that when sea ice drift is included in the simulation, the planet enter into a snowball state. All the surfaces are covered by ice and snow. For future work, I think there are two parts are very important. One is about radiation transfer, because the atmospheric composition, temperature, and pressure on exoplanets are very different from Earth. So the radiation transfer should be expand. These two panels show the comparison of radiation transfer model between GCM and the Lamb models. You can see that in both short wave and long wave, there are very large difference. I think Eric Wolf will talk more about this. The second part, I think the most important part is about the convection cloud schemes, because there are no observation yet. So cloud resolving model will be very useful. This is example in my group that show the near global cloud resolving simulation on tidal planets. You can see that the model show that in the subsoil region there are another clouds forms deep convection clouds. So this confirm that GCM results and also provide a benchmark for future GCM cloud scheme development. Okay, this is the end, the summary, and this is the end of my talk. Thank you for your listening. So any question?
So please put your questions in the chat again to leave time for the discussion at the end, but thank you, it's fascinating. So we'll move on to our next talk, which is Wang Ying Kang, a postdoc at MIT.
All right, let me start sharing my screen. Okay. So can everybody hear me and see my screen, see my slides?
Yes, all good.
Yeah.
Okay, perfect. So thank you so much for having me here. It's a great opportunity. I would like to share some of my work on high obliquity planets. So it's a different type of planets than what Jun Yang just talked about. It have so the obliquity is what brings us the season. So for example, on Earth we have an obliquity of 23.5 degree, and that bring us a very modest seasonal variability. But on high obliquity planets, the rotating axis of the planet is almost flipped over, and that will lead to extreme climate seasonal cycle, and also making the polar regions warmer than the equatorial region. So that's the key feature of these type of planets. So sorry, I myself can't see the title now, so let me move this thing around a little bit. Okay, so the reason why we are interested in these high obliquity planets is partially because that there's a lot of them in the universe, and partially because it's connected with paleoclimate. So shown here is the delta 018 signal after doing a Fourier transform, and this period of time is peaking from the early. It's peaked from the early Pleistocene. So what we find is that the frequency of the obliquity variations stands out from over all the other variabilities, and that indicates that obliquity could be a very strong factor that controls our climate. And also a very interesting experiment that have done by Jenkins and other people early on is that at the same, keeping all the other parameters exactly the same, but just changing the obliquity, the overall climate can change significantly. And it turns out that high obliquity planets with the same insolation can be tens of degrees warmer than the low obliquity equivalents. And that has been proposed to be a potential solution to the Van-Jansen paradox. Whether or not this is relevant to the over Earth history is not what I want to focus on today. But instead, what I want to talk about is why these high obliquity planets are generally warmer than the low obliquity planets. So one mechanism that have been proposed before is the Ice-albedo feedback. Because the high obliquity planets have strong seasonal cycles, so all latitudes receive strong and direct radiation from their star during some period of the year, and therefore it's hard to form a permanent ice gel, and that will lead to low ice coverage, lower albedo, and therefore generally warmer climate. So we will see, like, carefully examine whether that is indeed what's happening. So what we do here is we take ExoChem, thanks Eric for building this wonderful model up, and we put some water on the ground, and we fill the atmosphere with nitrogen, and then we gradually increase the insolation for a low obliquity scenario and for a high obliquity scenario. So shown on the right is the temperature shown in the dash curves as a function of insolation for high obliquity in red and low obliquity in blue. The temperature difference between the high and the low obliquity is shown by the solid curve with y-axis on the left. And as you can clearly see, no matter what insolation it is and what how much ice is on the surface, the high obliquity planets is always warmer than the low obliquity equivalent, and that is kind of a general feature, even when there's no ice at all. So then our question is, what causes that? So we will take one specific insolation and study that case and trying to figure out what makes the high obliquity warmer. So shown here is the annual mean surface temperature for high and low obliquity as a function of latitude, and mark the global mean temperature using the dashed lines. And you can see that I'm sorry. So the before. So if you go back, we will find that the high obliquity is warmer than the low obliquity equivalent by 15 Kelvin. So now here, the first thing we examine is the Ice-albedo feedback. So we turn it off by setting the Ice-albedo to be the same as the ocean. And what we find here is that the high obliquity is still warmer than the low obliquity equivalent by 9 degrees. It's smaller than before, but still most of the temperature difference still there. So there must be some other reasons makes the high obliquity planets, keeps the high obliquity planets warm. So what is that? So the next thing we examine is the cloud radiative effect. We turn that off by overriding the cloud radiative forcing. And what we find is that these high obliquity and low obliquity temperature difference disappears. And that tells us this cloud play a role in this warmness. And what happened, so we examined the cloud coverage and everything in this by month from the low obliquity and high obliquity experiment. And what we find is that in the low obliquity situation, there's no seasonal cycle, and therefore the star is always above the equator. And that is where the temperature is warmest in the surface, and there's very strong convections and NDCD that is locating right at the equator. And that forms the cloud, which will reflect all the sunlight direct back to the space. But on a high obliquity situation, for especially during the May season or the opposite season for the southern hemisphere, when the sun is moved to the around 60 degrees north, the ocean surface there is still very cold, and therefore the overall atmosphere circulation is subsiding there, and that will clear up the sky, allowing this sunlight to reach the surface. And that would lead to so I summarize here, in a high obliquity situation, there's more radiation reaches the surface because of the low cloud albedo. So we test this hypothesis by instead of turning off the cloud radiative effect completely, we just shut off the seasonal cycle. And what we find is that the temperature difference between high and low obliquity planets is small, and also this even becomes opposite than before. So now the low obliquity is warmer. And that indicates that it's indeed this seasonal cycle, and coupled with the cloud radiative effect leads to this the warmness on high obliquity planets. The next question so given that the high obliquity is warmer than the low obliquity equivalent, the next question that interests us is does that have any impact on the habitability, whether that will make the high obliquity planets more vulnerable to high insolation. So and to understand this question, we need to we need to study the stratospheric humidity, because that determines how quickly the water vapor water from that planet will escape to the space. And if that happens too quickly, the surface won't have any ocean left, and eventually will become inhabitable. So shown here is the specific humidity at 10 millibar from the high and the low obliquity experiments in red and the black respectively. And as you can see, they follow very different paths. In most of the insolations, the high obliquity planet stratosphere is about 2 or 3 orders magnitude more moister than the low obliquity equivalent. And if you look at the spatial pattern, On the right, we can see that the high obliquity is very moist in the high latitude, and low obliquity have the opposite kind of pattern. So in this experiment, we can turn on and off different feedbacks and surface and control the seasonal cycle, etc., to figure out why this difference happened. And we figure out there are three mechanisms causing this difference. The first is that the high obliquity planet is generally warmer than low obliquity equivalents, and that increase the saturated water vapor pressure. And the second is that because there is a seasonal, yes?
1 minute.
Okay,
Yeah,
because there's a seasonal, okay, so because there is a seasonal cycle, because there is a seasonal cycle, so the polar regions on the high obliquity planets can reach extremely high temperature, which cannot be achieved in the low obliquity equivalents, and that is a second contributor. And the third reason is that is because of some dynamic configuration. So shown here is on the left is the temperature profile for the high obliquity on the top and low obliquity on the bottom. And what happens is that in the low obliquity situation, because the Brule-Doppler circulation is pumping the water vapor into the stratosphere, so it have to go through these cold trap regions above the equator, and in that process, all the water vapor will be freezed out. And whatever left in the stratosphere is very dry. But in the high obliquity situation, first of all, the cold trap is not as strong, but also it's still located at the equator. So when the water vapor enters the stratosphere, it doesn't necessarily need to go through this cold trap filter, and that allows the water vapor to be high in the high obliquity situation. So clearly, I don't have the time to go through the dynamics, so I will just highlight some take homes from this part. So we also study the general circulation and dynamics on high obliquity planet. Because of the reversed meridian temperature gradient, there are a few consequences. First of all, the Rossby wave dynamics becomes more concentrated and constrained near the surface, and also that makes that changes the Hadley cell structure. So, and it's very interesting that we find when the temperature gradient reversed, instead of having atmosphere sinking at the equator, we still have upward motions. And that have to do with the wave pumping momentum from the equator to the mid latitude, and the circulation compared to the normal situation is much weaker. And also we find that as we gradually increase the insolation, these Hadley circulation and other overturning cells in the atmosphere changes its characteristics. So in the low insolation scenario, the overturning circulation is pumping air upwards in the equator, but in a very high insolation, when the climate is very warm, the thermal component dominant, and that drives sinking motion at the equator. So these regime changing have some observation impacts. Okay, so that's all. Thanks.
Thank you. Obvious, we need another meeting. We have so much interesting things. So our next talk is Thomas Fauché, who's a planetary scientist at NASA Goddard Space Flight Center.
Hi, everyone. Can you hear me?
Yes, perfect.
Great. Thank you for having me today. It's a very, very interesting session. So I'm about to share presentation. All right. Okay. So hi, everyone. Yeah, I'm Thomas Fauché. I'm a planetary scientist at Goddard. And today I'm going to discuss about how model intercomparison are and will be very useful for exoplanets. And so first of all, you may have noticed that every time we discover a new planet, a rocky exoplanet inside the habitable zone, It's really a little bit the rush from the community to be the first to simulate the potential climate and habitability of this planet. So it's completely fine. It's really great. But what we want to be sure as well is that the conclusion that are given by a given model are no model dependent. But basically that all those different GCM will agree between each other. And so when we look at the literature, for example, here for the TRAPPIST-1 system and TRAPPIST-1e, well, there are several studies that have a look at this planet. And what we can see in general, that they agree globally on the habitability of this planet, but still the surface temperature, for instance, for this different study, are slightly different. The mean value could be offset by a few tens of Kelvin, and also the distribution of the temperature around the planet could be different, even if the initial conditions are exactly the same between the GCMs. There is here also the case 3D is showing a dynamic ocean, which is different from the other model. But yeah, anyway, we have a lot of parameterization that can at the end provide different results. And so the question is like, how do we know which model is closer to the truth without having data yet? Because we need to probably wait for the James Webb Space Telescope to give us some information about those planets. And so, but before we can't, but what we can do right now is to compare the model between each other, to quantify differences between them, and so to bracket the prediction between mean and max value between various GCMs, and therefore providing to observer more robust and less model-dependent prediction and data interpretation. And so that kind of approach has been done, of course, for many decades by the Earth science community. And I can highlight the CEMIP, the Couple Model Intercomparison Project, that is, of course, very, very useful. And here, I'm just showing that we have a lot of different models that are on board CEMIP. This is just showing the equilibrium climate sensitivity on the y-axis. It's not really important. I just wanted to show that we have many models, and well, the outputs slightly differ as well. And so, of course, CEMIP was also used and still used to predict the future climate of Earth. And what is very interesting is when we have many models, then we can have a model range where we can, again, bracket the prediction and be less model dependent. And so we had intercomparison for Earth, but also in the solar system. We have several for, I think, Mars and also Venus. But one I wanted to highlight here is a very interesting one for Titan, which has been done by Laura et al. In 2019. And the objective was to prepare the NASA Dragonfly mission. And so 3 GCM were on board, the EPSL Titan, the Colon Titan, and the Titan atmospheric model. And so from this intercomparison, there are a few key results. Like in general, they have good agreements on atmospheric structure and circulation that are predicted by those 3 models, and also for the methane content at low altitude. But there are some disagreement versus the data on the winds over the boundary layer. I mean, the winds are quite difficult sometimes to simulate, and also they have different boundary layer parameterization between the model. But overall, they give similar simulated environment that observed with the Huygens mission, except for the methane cycle, which is highlighted by this plot here, where we see the methane precipitation, and especially the EPSL model here show much more precipitation of methane than the other model, and also at different places. So at the dawn of JWST, we need to start intermodal comparison for exoplanet as well. And so the first intercomparison that have been done were by Jun Yang, that just presented a few minutes before me. And the first one was about a 1D model and the difference in the water-vapor relative transfer. And this intercomparison provided a very interesting result that helped after the community, because they found that there are many atmospheric models that don't resolve enough their near-infrared and water absorption band and windows, because it's fine for a planet around the sun, a G star, but if you put a planet around a star which is much colder, much more red, then you need to better resolve the infrared water absorption bands. And that has been an important finding for this intercomparison, and then the model has been adapted to that. Then June and colleague follow up on 2019 with a GCM intercomparison, this time for tidally locked planets. And they found that between the different GCMs, there are discrepancies between 20 to 30 Kelvin on surface temperature. That was mostly due to differences in atmospheric dynamic, clouds, and relative transfer, but mostly clouds because they are quite difficult to parameterize in GCMs. And so in our case, at Goddard, we had, and Goddard and elsewhere, we had the TRAPPIST habitable atmosphere intercomparison. And the objective here was really to focus on few cases and see how different GCMs would predict at the end atmospheric outputs that may predict different observations for James Webb. So basically, we take the GCM outputs and then we feed them to a spectrum generator to simulate observation, and we see if we found differences on those simulated observations. We had one planet, which is TRAPPIST-1e, because it's probably the best target for JWST atmospheric characterization, and 4 GCM on board. Rocky 3D from NASA GIS, ExoCam by Eric Wolf, so it's a CESM 1.2.1 adapted for exoplanets by Eric, the Unify model in a Met Office, and the LMD generic model in France. And we have 4 different cases. On the left, we have 2 benchmark cases where we have no water on the surface at all. We have a modern enough atmospheric composition and 1 bar CO2. And we look at those cases in order to check differences in relative transfer, planetary boundary layer, and dynamical core. And then we move on the same atmospheric composition on the right, but this time we fully cover our planet with an ocean. And so we look at the moist convection and clouds and all those differences. And so we have published in 2020 the protocol for this intercomparison. And now we are about to write a trilogy of 3 papers that will really debrief this intercomparison, and actually more to come. So to quickly show some of the results, here what you can see are surface temperature maps that are centered at the substellar point for each of the GCM. So you have LMDG on the top left, then ExoCam, Rocky 3D, and UM. So above the temperature map, we have the 250 hectopascal winds. And under each subplot, you can see the minimum value, mean, and max value of surface temperature. So what we can see quickly there that, well, they agree roughly between each other, but you can see, for example, UM, it's much colder at some location there and there. And so the temperature distribution is different. Also, we can see some change in the dynamic, like the winds here are starting to form some gears on the left side by Rocky 3D, which can be a sign of a slightly slower rotation of the atmosphere for this planet.
Thomas, 2 minutes.
So, yeah. And so now when we had all those atmospheric outputs for the modern Earth, we say, okay, if we feed them to a spectrum generator to predict what James Webb could see from this planet, what are we going to get? We got that. Here, what we are plotting is the atmospheric transit depth on the left as a function of the wavelength for each of the atmospheric output provided by this GCM. As you can see, we have a spectrum with different absorption lines. And what is the most different between each of these GCM is actually the continuum level. Because the continuum level for a transmission spectroscopy is going to be driven by the altitude of the cloud deck. So if you have a model that predicts higher clouds and thick, then you're going to have a higher continuum. It's the case here for ExoCam, for instance. And so it's going to reduce your absorption line from the bottom. And because you reduce the amplitude of the line, then you reduce its detectability. And at the end, if you try to predict how many transits you will need by James Webb to detect this atmosphere, looking at CO2, well, you will need 20, for example, for ExoCam and MDG, you will need 16 for Rocky 3D and UM that have lower clouds. So it's a 20% difference. It's not dramatic, but still it can, shift you from different category of proposal when you're asking for observation time and transits. And so for that, we had a Thai workshop that happened in last September. We have several people here on the call that participated to this workshop. And we had 3D and climate modelers, about 125 people. And we have a special issue right now on the Planetary Science Journal that collects 7 papers debriefing Thai. And so to conclude, what next? We are working on a larger project. We are still looking with the food acronym, climates using iterative suites of intercomparison nested for exoplanet studies, cuisines. where here the objective is actually to host many more intercomparison like TIE for exoplanets. And so Cuisine will be a meta framework, so framework hosting frameworks to compare, benchmark, and validate exoplanet models. So they could be GCMs, it could be energy balance model, radiative transfer, 1D photochemical models, anything. But we want to help the community to benchmark them and to provide those benchmarks for a long, long time for future models to come as well. And so if you're interested, we are going to have, it's not yet announced, but a workshop on this Cuisine project that's going to be held virtually in September. We are going to announce it very soon, but if you're very interested, also please send me an email. And yeah, I will take any question.
Well, thanks, Thomas. So we'll move on to the last two talks. The next one is Howard Chen, a PhD student at Northwest University. He had to cancel here right at the last second, but Eric Wolf agreed to give his talk as far as I know. So Eric, if you could give Howard's talk, and then following that, Eric Wolf, who's a research scientist at University of Colorado Boulder, will give his talk.
Hello, sorry about that. Can you see the screen?
Yes.
Okay, great. So hi everyone, I'm Eric Wolf. Sorry, Howard unfortunately couldn't make it today. He's traveling. He smartly spent the pandemic in his native Taiwan with his family, but is traveling back stateside. So he couldn't give this talk today. So I'm gonna give it on his behalf. So characterizing atmospheres. Thomas, sorry about that. I just hit the wrong damn button. Oh, hopefully we're almost done with these virtual conferences. My mistake. View slideshow. All right, we should be back. So Thomas talked a little bit about atmospheric characterization through transit spectroscopy from the TIE project. And it really combines three different aspects: the composition of the atmosphere, which has chemistry, the chemistry of the atmosphere, the chemical composition, and also clouds, which play an outsized role, which Thomas talked a lot about and will be in the papers about the TIE project. So traditionally, such transmission spectroscopy type works and thinking about the chemistry of exoplanet atmospheres, photochemistry affected by the different stellar types, has been the purview of 1D photochemical models, which are fast and have well-defined chemistry and flexible chemistries for a variety of atmospheric types. And then 3D models have been used for modeling the climate and clouds of extrasolar planets. Shown here are some results of tidally locked planets where you have that substellar point that develops a thick cloud deck, which June has talked about, and a warm spot right at the middle of the planet. However, we really need to start combining these two aspects together, but it's easier said than done. So Howard has done his PhD work at Northwestern University using the Wacom model to study the chemistry and climate of tidally locked exoplanets around M-dwarf stars. So combining these two elements. So the atmospheric circulation on tidally locked planets is very different from that on Earth. So the advection of species, as well as the different stellar spectra coming in, can affect your atmospheric chemistry and also gradients of where you see atmospheric species existing. So on the left, we have an Earth-like planet with your 3 weaker meridional cells of circulation. And then for a tidally locked planet, you tend to see this one big, strong meridional circulation and higher gradients between day to night. So Howard has used Wacom, which Wacom obviously has been developed for the modern Earth and is includes chemistry, and karma is well linked to it for different hazes or for different types of aerosols. It has a high model top. I guess one of the problems with exoplanet modeling is the more complex the model gets, the harder it is to adapt and modify it to suit different exoplanets with different stellar spectra and different atmospheric compositions. Gets to be particularly difficult for say with Wacom and Mozart, trying to force atmospheres that have wildly different CO2 than the modern day, for instance. So Howard has published a series of 3 papers. The first one in AppJ Letters using CamChem, which was kind of a proof of concept that on these tidally locked planets, you do end up with day to night asymmetries in important possible biosignatures for terrestrial exosolar planets. The second paper used Wacom, and that was in AppJ, and it examined the combination of atmospheric dynamics at different spin rates with photochemistry for different stars, looking at moist greenhouse atmospheres. Moist greenhouse atmospheres are those, it's a term, an ancient term defined by Jim Casting, of when you get a certain amount of water vapor in the stratosphere, typically above about 1,000 ppm, I think it is. You can start photolyzing your water and then losing and leaking your hydrogen to space at rates which are geologically significant, that you can actually leak away a whole Earth ocean of water within several billion years. So Howard was looking at these moist greenhouse atmospheres with Wacom, where you can actually model the upper atmosphere and the chemistry quite well, and the rates at which H2O is being dissociated. And then finally, published in Nature Astronomy just recently, Howard used Wacom using its features for simulating flares and including solar energetic protons for exoplanets around G, K, and M dwarf stars, using flaring rates and strengths derived from observations using the TESS satellite. So to kind of show some of the key plots here, this is from Howard's first paper looking at patterns of dimethyl sulfide emissions compared to an Earth-like case with global dimethyl sulfide, and compared to a tidally locked planet where you may only have emission on the day side. You start seeing these definite the change in the gradients from equator to pole, from day side to night side. Same in ozone as well. You can see that on the left-hand panel for a low mass star and tidally locked planet, you see this minimum in ozone right on where the sun is shining, and ozone tends to collect on the night side of the planet. So I'll have to refer you to Howard's papers for a much more in-depth discussion of these topics. I'm kind of giving a cursory overview of his entire thesis work at the moment. In his 2019 paper, he looked at this casting moist greenhouse effect, where instead of in the casting mode, when water gets above mixing ratio of 10 to the -3 in the stratosphere, we kind of hand wave and say that water loss could be significant. But however, with Wacom, you can actually calculate how much water is being photolyzed, how much hydrogen is being produced, because hydrogen is what's leaking away to space, not water. So in these experiments using stellar spectra from a variety of stars, Howard found that it's really the stellar activity that drives the photolysis of water vapor. So it's active stars, you can have water loss to space at significant rates and dry out planets. However, if you have a quiet star, that water ocean water and water in the atmosphere will stick around for quite a long time. So the casting, hand waving limit of the moist greenhouse is really appropriate thinking about active stars and not quiet stars.
2 minutes, Eric.
Okay, I will kind of jump ahead a little bit. So Howard, in collaboration with Zhupchong Zhan at MIT, calculated a bunch of transmission spectra and emission spectra, which I'm not going to go into. I'm going to, I guess, talk a little bit briefly about Howard's latest paper in Nature Astronomy, where he used Wackham's flare capabilities to simulate flares onto Earth compositioned planets around different stars, including Wackham has the feature where you can control where the latitudes at which the solar energetic protons can impinge on the planet. So with a magnetic field, these energetic protons are kept towards the poles. However, it's thought that some of these tidally locked planets may have limited magnetic fields. So the solar wind and the charged particles may just slam right into the planet unprotected instead of funneling those particles to the poles. So, and this figure kind of shows the idea there. For a G star, this is. I should also mention that flares on M dwarf stars can be much more powerful than from the sun. So first, for a magnetized planet around a G star, this is nitrous oxide. At the flare peak, you can see pre-flare, flare peak, and then the post-flare and the 300-day mean magnetized. You see most of the action happening at the poles here. But for an unmagnetized planet around M dwarf star, you can see that the whole planet, or the whole day side of the planet, is affected, and you can actually cause a state change that doesn't go away. Where on Earth, the Earth-Sun system, you may have one strong flare that occurs, and then that hits the Earth, and then a long time period with nothing, so the chemistry can damp back down. But for these M stars, these big flares can hit at high frequencies enough that you actually pump the atmosphere into a different state, comparing pre-flare to post-flare and then 300-day mean, because these larger flares are actually hitting, I don't know the number off the top of my head, but on frequencies of less than 300 days, you're continually pumping up the chemistry. So, and changing the state of the atmosphere composition based on flares, and strong flares at high rates of impinging. So Howard is going to he accepted a postdoc at the Goddard Space Flight Center, the NPP postdoc, and he's going to be continuing to work with myself, and then also Dan Marsh, to do different projects extending the capabilities of Wackham for studying extrasolar planets. These include trying to put in anoxic chemistry into Mozart with a preprocessor. So this will be a really big, a big positive step to allow us to model the chemistry of different types of planets, not just oxygenated ones. And he's also working on the implementation of prognostic high energy ion reactions with Vladimir Pershian and Hanli Liu. So I think that's the end of Howard's talk. So hey, Howard is a very talented student, soon to be PhD graduate. I'm sorry he couldn't be here today with us, but he is definitely going to be a major contributor to CAM, CESM, and Wackham exoplanet work. Already has been so, and will continue to be in the future. So,
okay,
sorry he's
so
not here today.
Yeah, so we'll go to the last talk here, and
okay,
and just okay. Again,
all right.
And I'll give you a 2-minute warning again.
Okay, great. Can you see my screen good?
Yes, all good.
All right. So hi everyone, I'm Eric Wolf again. So I'm going to talk about ExoCam, an extension to CESM 1.2.1 for simulating exoplanet atmospheres. You probably heard the name ExoCam bantered about a few times earlier in the day today, which I'm happy about. So I'm at CU Boulder and LASP. I also have the NASA logo up here because despite CAM being an NCAR NSF branch of science funding, NASA has funded the development work for ExoCam over the last decade or so. So what is ExoCam? So it's a model extension to NCAR CESM 1.2.1 that facilitates a variety of exoplanet climate modeling applications. While most of the applications tend to be in these idealized regimes, aquaplanets, land planets, simple atmospheric compositions, nitrogen and water vapor, or just CO2 and water vapor. It can be surprisingly difficult, especially for people new to the field and students, to try to take a major climate model from a national lab and just say, okay, I want to strip away all the complications. I just want to do something really simple in the context of an idealized exoplanet world. So that's where ExoCam kind of comes in. So it's easily installable on top of CESM 1.2.1. It contains source code modifications, initial conditions files, name lists, CESM util scripts, initial conditions and analysis scripts, things like that. So ExoCam grew out of my graduate work and early postdoc, post-PhD projects. And here's just a gratuitous video of a K2-18b simulated with 40% H2 in its atmosphere, that water vapor at the 200 millibar level. So what can ExoCam do? Currently, out of the box, it supports compositions of nitrogen, water vapor, CO2, methane, and hydrogen for surface pressures of 0.25 up to 10 bars. I think actually recently one of Aomawa's students has been has gotten the model to run down to 0.1 bar as well. So that we're kind of increasing the bounds there. Temperatures between 100 and 500 K, that's in the radiative transfer limits. And if you use a dry planet, you can tend to get to hot climates, but if you have an aqua planet, you tend to run into numerical instabilities and runaway greenhouses and things like that. Surface types, generally we're thinking about idealized. We don't know much about exoplanet surfaces, so we tend to think about idealized configurations. Aquaplanet slab oceans, there's a Q-flux ocean, land planet with Earth continents. I've hooked up ExoCam to the dynamic ocean model before as well, but I have not had the patience to work through the paleoclimate toolkit to actually change the boundary conditions, because the paleoclimate toolkit, for those familiar, works in binary files, which is, I just lost patience. But you can run it with the point is ExoCam can be run with a dynamic ocean model as well. ExoCam provides a number of stellar spectra between 2600 and 6600 K. It collects in one module, it collects orbital planet parameters and planet parameters that are all in one place. You can configure ExoCam in different ways. Typically, I run it with CAM4 and the finite volume scheme, but I run it with the spectral element scheme. You can leverage some Morrison and Gettleman cloud physics and karma and different things like that as well. So how is it structured? So ExoCam actually is split into two different GitHub distributions. First, there's ExoCam, and second, there's ExoRT. So I'll start with ExoRT first. It's the radiation scheme, and I decided to split it off from ExoCam a number of years back into its own version so that it facilitates development. So there's a 1D offline version of the radiation scheme, so you can just run the RT by itself and work on developing it, and then create linkable versions that link with ExoCam readily. So ExoRT contains all the absorption data, 1D test profiles, IDL scripts to do this sort of thing. And as far as its general function, while radiation is perhaps the most important upgrade in the package, having a flexible and easy to work with radiation scheme is critical for exoplanet modeling, where things like the dynamical core and surface boundary conditions and cloud physics, which is also a very important thing, we tend to reuse them from the Earth model. To start getting to weirder atmospheres, you start needing to expand on your radiation scheme if you want to do stuff like a pure CO2 atmosphere, or a sub-Neptune atmosphere with fractions of hydrogen and things like that. So, and it's so then on the ExoCam side, so ExoCam contains the standard CESM machinery, source mods, name lists, etc. And then its functions are, it has a collection of smaller fixes I've acquired over the years in different places in the code, which I won't spend my minutes describing at the moment. And then it also collects into a single build time module many of these important geophysical and atmospheric parameters that you're interested in. So I know there's numerous ways you could set things via name lists in different parts of the code. This just kind of collects everything into one place, that if you're, okay, you just want to model an exoplanet, just go to the one file and change your planet radius and its spin rate and the amount of CO2 all in one place, and it overrides everything else. So with ExoCam, you copy all the files to the right places after you already have CESM 1.2.1. And then for XORT, typically I include it via the user_src option. However, you could just copy all the files into the source mods src.cam file with cam directory if you wanted to. So where to get it? So you got to get CSM 1.2 first, and then on my GitHub site, you can get both ExoCam and XORT. So these were first made available to the public on GitHub in November 2018. And I think it's important to note that originally I put these on GitHub simply to keep myself organized as I was starting to splinter into different projects. And lo and behold, other people started to find it useful and started to use it. So to date, there are 32 papers, including what I'll call some proto-ExoCam papers I wrote as a grad student by 17 different lead authors. So there's definitely been, interest in the community and an interest and value found in it in the community. So, okay,
Eric,
great.
2 minutes.
Good. So the latest, so recently I just did a big overhaul of the radiative transfer scheme. I've improved it over the years. Now it's up to date with HITRAN in 2016, all the latest collision absorption. I switched out the gas overlap scheme to the equivalent extinction gas overlap, which means you don't need to make these massive pre-mixed absorption coefficient tables. You can just do one gas at a time, and the dominant gas is dynamically selected. And then for correlated K, I've been using the Helios K GPU driven sorter from Kevin Hang's group in Bern, which is just incredibly, just blisteringly fast. So combined between the Helios K and the extinction, equivalent extinction, modification of the radiative transfer now can be pretty fast. You still have to, unlike a model like Socrates, which handles all the back end stuff for you, if you want to add a gas, you have to get your hands dirty a little bit, but making the K coefficients with Helios K can take a matter of minutes to hours, and you can really get things done fast. So I'm excited about that update. And here's just a proof I did something. This is for a pure CO2 atmosphere, 2 bars, the outgoing long wave radiation, comparing SMART to Socrates to N68 equib is just a version tag in XORT now, and you can see that they do pretty well. So the new RT and ExoCam and Socrates actually get almost the same exact answer, a little bit different than SMART, which is line by line. I surmise the difference involves the line wind treatments between the two, but nonetheless, you can see going to say a 2-bar pure atmosphere, you need to start expanding the flexibility of your radiative transfer code. So the future, so I have a couple of funded projects, an early, which will hopefully dovetail back into ExoCam stuff, which will be made public. So I have a funded early Mars project. There already is a Mars cam, but I'm going to kind of integrate some of the functionality back into ExoCam, including CO2 surface and cloud condensation, karma cloud and dust applications, and some low pressure atmospheric bug fixes and files that I've already run across. For the funded H2 rich planets project, these are the type planets JWST is going to see. So dovetail development stuff. We're talking expansion of the K coefficient sets to higher pressures and temperatures, some new gases, helium, ammonia, and whatever high pressure atmosphere bugs and stuff and files I've run into along the way. Finally, funded TOI 700D simulations, which will incorporate more work with fractal hazes, with karma. And then, so finally to finish, so I think it's important to note that, ExoCam is merely, I would say, a convenient hack based on my personal work, which I put on GitHub, which has fortunately been useful for other people. I don't proclaim that it's the greatest, the best way to do things. In fact, perhaps probably not with CESM, especially now, as Dan mentioned at the beginning, So CESM2 is now forkable on GitHub, unlike when I was working with CESM 1.2, and CESM is the community Earth system model. And so right now, ExoCam is kind of my little toy model that I post on GitHub. But I think all of us would be benefited perhaps by moving past ExoCam and pulling together towards like an official Planet CESM branch, perhaps forked off of CESM2. I know easier said than done. It's a ton of work and structure and needs to be done, but having multiple people and all the interest today of having multiple people feeding into and developing the branch, I think would really start to gain us more traction, as opposed to, I love ExoCam. It's taken me this far in my career, but I've kind of reached that wall of productivity and tasks and things to do that it's hard to keep it floating as the only contributor official contributor at the moment. So I think that it would be really cool if we could make something bigger with the community, with everyone contributing. So that finishes my talk. So thank you all for listening to my talk, and also my talk on behalf of Howard, who put together those slides. So thank you.
So I just want to thank all the speakers. A lot of exciting talks. I learned a lot, spurred my imagination. Remind you that these are all recorded on YouTube, so you can go back and look at them. And I'm going to turn it over to Dan now for the discussion. We've gone a bit over, quite a bit over. I did look at the schedule, and there's nothing after this in the CESM workshop. So if people can stay and want to stay, we could go a little bit longer, though I realize it's different time zones for some of you, so we understand. So Dan.
All right. Hopefully you can see that and you can hear me all right. I have a few notes here that I thought might spur some discussion. I first of all want to thank all the speakers for some really interesting talks, and the fact that we went over, I think, just indicates that we need a larger venue. We need more time to talk about all the exciting work that's going on with CSM and in this area. So I just thought that perhaps we could have some structured discussion in two areas. One is sort of this idea about co-development, about, as Eric pointed out, maybe thinking about how all of this work could be better coordinated and what would be projects that we could work together on within the sort of CSM development paradigm of forking and pushing things back and moving everything along. So I have a big list here of not only just things to do, but perhaps new opportunities that have come along since CSM 1.2. And then the second slide, I thought we could have a discussion a little bit about how to proceed. But I just want to point out that I think there's some really nice stuff that's happening within CSM 2. We have this simplified models project in which a lot of these simpler model cases may be easier to adapt to other planets, or to focus on things like the dynamical variability, high obliquity orbits, those sort of things. And the fact is that we're talking about containerizing these models means that you may be able to, or hopefully be able to take some of these simpler models, grab a container, and have it running on your laptop within minutes, and then you can play and create your own worlds. So that's sort of exciting. There's been a lot of talk at this meeting about things that are hopefully making the physics interface easier, using such things as CCPP. And in the future, maybe it might be easier to bring in different types of radiative transfer code. But though I think it's something along the lines of this model into comparison project. I think understanding structural uncertainty in sort of climate prediction can be applied to exoplanets. So we just saw quite an interesting difference there between two climate models in the tie into comparison that both run the same radiative transfer code, but have very different surface temperatures. So that was an interesting thing. So why are they different? Is it to do with the dynamical core? It's not clear. And then I just think that there's some work in the paleo community. This isn't just all about exoplanets, right? This is about pushing the model into regimes that are not typical or tuned for in CAM and CSM. And so there's some discussions about, I know that some development in the paleo group about thinking about simplified land models. So as the standard climate model runs off and starts to have things like interactive crops and those sort of things, we need to keep some sort of simpler land components, or a way to take that model and apply it to, say, ice-covered or rocky planet. And so, so there's that idea there. There was some discussion about atmospheric loss process, and I think around active stars, we really need to start leveraging some of the work that's been talked about in terms of coupling WACM, say, to magnetosphere models and looking at atmospheric loss processes around active stars. So maybe there's an overlap there and some opportunities. And then just as we've seen a few examples of taking the output from the model and using that to generate spectra that can help in the design of new instruments. So those are some ideas. I maybe have a discussion about that now for 5 or 10 minutes, and then we could talk about next steps after that. Anyone want to comment?
Hi, Dan.
So
So sorry for.
Oh, you can raise your hand in the reactions, or just whoever. Eric, go ahead.
Oh, sorry, I'm kind of half trying to answer the chats, and I think I spammed you, Dan, on direct messages, and I need to copy them back to everybody. But as I kind of finish at the end of my talk, I'd love to see a broader community involvement, but I know it's not easy. It's not easy funding wise. It's not easy organization wise, and not having really a native home. As I said, that my ExoCam work has been NASA funded, not NCAR NSF funded. So it's I don't really know. I would love to see us have a forked official CESM2 planet branch that we can collect all the work that we're doing together. But as far as the organizational structure, I almost would dare to say that's sort of above my pay grade about, well, who's leading this thing, who's making the key decisions. It's I mean, I guess that's why we're here today, to try to start chipping away at some of those things.
Yeah, I think that moving CESM to GitHub and really sort of embracing open source and co-development means that we don't need the blessing of NSF, who may raise an eyebrow about NCAR doing a lot of exoplanet work, but the infrastructure is there, and we can leverage that and embrace the open source development, and they will see the benefit, I think, when we start bringing in these new codes that perhaps allow us to understand things like structural uncertainty and climate prediction. So I think it's I think you've done an amazing job of with ExoCam, but I'd like to maybe share that burden among the community and try and have everyone contribute together.
Yeah, I agree. I definitely agree.
So we have a question there. Is it Marisa?
Yep. I guess I just am throwing in one more vote for if we could bring ExoCam into a sort of branched off CESM2 state on GitHub, that would allow us to leverage a lot of other development that's going on. So there is an idealized land surface model, it's called SLIM, that runs in place of CLM. And we at one point actually with Andrew Rushby tried to couple it to ExoCam, but it's a bit of a, all of the coupling infrastructure has changed so much in the last like 5 years that it was a bit of a nightmare. But that would let, having it on the CESM2 branch would let us borrow things like that are already there.
Yeah,
Right.
I'd love to do that. Things have just become time limiting as far as actually getting to it. I've been meaning to. It took me forever to jump from CAM 3 to CESM 1, and now they're going to be on to CESM 3 by the time I get to CESM 2.
I know it's hard. It's a lot of work.
It's hard. Yeah.
And perhaps, but that's the nice thing about GitHub is I think we can keep them in track and just keep pushing and updating the model as we go along, and not have them diverge so far, but just sort of keep them in parallel. Brian, you had a question, question.
I just wanted to also agree with you, Dan, that I think that we can bring a lot of this into the simpler models approach. I mean, we've done a lot to make it easier, I think, to do a lot of these changes. And I think Peter mentioned in the chat that we have changes on the dynamic side too that should make it easier to make these things. So it might not even be a fork of CESM. It might just be making a few small changes that would actually enable things like Eric's RT to be configured in CCPP and things like that. I think it wouldn't, it's not necessarily a separate model. It might just be new comp sets with some added features.
Yeah, I mean, most of these changes in gravity, rotation period, radius are now just nameless variables. So, and hopefully, I mean, this is always the difficult part, is that those dependencies are now put into one place in the model. And so you don't have to find everywhere where the Earth's gas constant has been defined or something like that. So yeah, it could be that there's at least something simpler that represents, say, Mars, which is it's essentially just nameless selection.
So Eric has his hand up. Eric DeWeaver.
Yeah, hi. I just want to respond to Eric Wolf, who said that he was looking for the blessing of NSF, and I work at NSF, and I'm happy to bless this on behalf of NSF. But my sense of it is that you don't actually nobody needs NSF's blessing. What you need is NSF's money. I mean, it is a funding agency after all. And I think the key to NSF's money, I mean, there's a few things here. First of all, how much does stuff cost? Because it seems to me as though usually when you want to do stuff with CESM, the issue is that the software engineering actually does have to be done at NCAR, because that way it'll be done in a way that's compatible with everything else. And the other thing is that, NSF always sort of somehow prides itself on or claims to be community driven. And so I think the key to NSF's money is to sort of identify how this fits in to some concept of the community that NSF funds, because, traditionally, I think NSF has taken the view that exoplanets are the purview of NASA. And I don't know why that's not true. I don't know why. I don't know what aspects of exoplanet science are not being covered by NASA. And so I think, getting clarity on where NSF really fits into a picture that I think ought to be to some extent driven by NASA. And secondly, kind of defining, what the community is. Those would be things that we would want to talk about.
Thanks, Eric. If I could just comment. So I think that, you're right. NASA does have a large and ever increasing funding pie for exoplanet science in a variety of facets. And they have their own 3D model for exoplanets based off the model E2 that they're putting money towards. But amongst this biased crowd, so I get a little bit of money from that team as well. Amongst this biased crowd, I could say, honestly, without having to hide my true feelings, I feel like CESM is a lot better model than the model E2. So I wouldn't say that in that crowd, but I like the CESM model framework a lot better. People I know who use it seem to think it's a much more user-friendly model. The way it, and now that it's on GitHub, I think it's even better. So while NASA does have the exoplanet thing covered, CESM provides another, you can never have too many models which all disagree with each other, especially when we get into planets and exoplanets and things diverge. And I think CESM is a very powerful tool, a more powerful tool than the Model E2 version that NASA is funding at the moment. So
it may also be that there are interesting sort of, science taxonomy ways of getting at this question. And one of the things that we do sometimes in my program, although it's not really our thing, is snowball Earth projects. People taking CESM or something similar and seeing what happens when you cover the Earth with snow and ice and all that. And there are these interesting projects about refugia for life in the snowball time and so on. Other things that we have certain things under one roof that NASA may not. The business of putting flaring into Wacom X, for instance, it's easy for us to do because the geospace part of NSF sits right in the same section as the sort of regular atmospheric part of NSF. And so that's kind of makes life easier for kind of mixing and matching some things. I don't know that you would ever have the same sophistication for an exoplanet model that Wacom X gives you in looking at the upper atmosphere. So there are those kinds of considerations that go along with it. And another one is that a lot of people that we fund to do regular climate dynamics dabble in exoplanets, and we never discourage that. I mean, if somebody wants to do exoplanets on the side, and I happen to notice in one of their project reports to me that they're working on exoplanets, we're not going to wag my finger at them and say, no, don't do that, you're out of scope. Because I sort of understand that we have to let people's interests expand in the sense, as much as we can in the directions that they follow. So it is kind of, it's partly a technical question about, who has the better model and who has the better modeling framework, but there's other aspects of how we conceive of the science and how we sort of approach it that might be worth considering.
So Peter has his hand up, Lauritsen.
Yeah, I just wanted to echo a lot that's been said, but just pointing out from, like, I'm a CAM model developer, and I really see huge benefits in improving our codes by, bringing, supporting exoplanets and so on. We need to generalize our codes more, and that really improves our code. So if in some way can, in a more official way, support exoplanets within CESM, I think it's really a win-win situation. There is, of course, the aspect of the software engineering support from the NCAR side that obviously needs to be funded. And then also from the science side, I was looped into simulation of superrotation on planets, where they found really interesting sensitivity to the numerics, where they showed if your dicore cannot conserve angular momentum, you cannot simulate superrotation. And that's really exciting science that can be done. So I really hope that this can happen. And if the code does say that NCAR, then it's easier to move the code along with whatever is happening with CESM, instead of, I assume Eric has to work at night and, I don't know, during the night just to keep up with everything that's happening. If it's supported in a more official way, then, these things can much easier move forward. So just wanted to express that.
Colin has questions, and then Gokhan, a point to make. Yeah, please.
Yeah, I think this was an encouraging point to make. Is if, as well as exoplanets, which are like way away from the core business of contemporary climate change, I think some of the modifications we need for higher greenhouse gases, warmer, colder climates, apply to Earth's paleoclimate, and that is the same physics on the same planet. And if the model can get that right, then we might actually believe model results for future climate, which there's no reason to believe at the moment if we can't simulate past climate. So I think there's a really important argument there that opening up the scope of what we can run this model for and really trust it actually should feed back into increasing the robustness of results for anthropogenic climate change. I know the paleoclimate working group, work a lot on that, but I think we can go to some deeper paleoclimate cases, do some weirder stuff with different climate states, and I think that really should feed back into the core mission of the model.
Yeah, and from a selfish viewpoint, the more people working on adding these, things like the radiative transfer that is capable of simulating very different atmospheres, the more I'm allowed to use the model for Earth's atmosphere. So So I think it could be a two-way street here, in which it's not simply that we're trying to serve the astronomy community here, that we benefit both ways, as you both, Peter and Colin, point out. Gokhan, you have a question?
Well, I was just jumping from the other cross-working group, and it's interesting that the discussion is going in the same way. And they were saying that NCAR and CESM and NSF should be essentially be the hub for machine learning, and we should be supporting the community at really high levels. So I'm glad that the same conclusion is coming essentially. So we'll be, Eric, you are listening, right?
Yes, I hear you. You know, and should money fall from the sky, it's good to have a basket to collect it in, right? I mean, we don't know how much longer Biden is going to rule the roost before the House and Senate flip and we go back to sort of government shutdowns and things like that. But in the event that there's interest in, you know, increasing the funding to, you know, to climate science of all kinds, I think it is, you know, it is worth considering what would be the appropriate things for NCAR to provide in that scenario. And, you know, the problem with this kind of stuff is that you can work all night, you know, dreaming and scheming and concocting ways, and then the money doesn't materialize for one reason or another. And that's life in the federal government, of course. But yeah, I mean, I think you know, the issue of, at some point, this becomes a political process, right? I mean, you can only fit so many people in NCAR. If you want to have different model configurations, they all basically compete for the same machine cycles and software engineering time and things like that. So, you know, there are cautionary sort of notes to sound in terms of wanting NCAR to be the nexus of all things. But it is worth, this is the time to be thinking about that stuff.
Agreed. Thank you.
So maybe that's a good way to tie into how we actually move this forward. So let me just put up a slide here that I thought might be some ideas here about how to move this infrastructure for alternative Earths forward. So one idea would be to just create a community FAQ around adapting CESM2. I think everyone probably goes to Christine Shields' FAQ when they want to do something a little extreme with in paleo. She has a great thing there, and if they can't figure it out, then they go on and they start posting questions on the bulletin board, and then this idea that maybe we can start thinking about adding extensions to the simpler models to the repository. If this doesn't require necessarily any kind of blessing from CESM. I mean, it's something that it's a community model. Anyone can contribute to it. It's not the one we'll be running for CMIP 7, but it doesn't mean people can't contribute. We may, given the excitement of it and the fact we ran out of time and everyone was even just given 10 minutes and we easily filled 2 hours here. I think maybe thinking about how we could reach out and have something to do with CSM at planetary workshops. And then of course, you know, money does help. So we should think about coordinating proposals. I don't know, I'm not big on formal structures. I think usually if you have a group of people that are excited about something, they get together and they start working on projects. But at some point, maybe this grows into something where we do need more formal structure. I don't know. And, you know, the bigger it gets, yes, we may be imposing on limited resources and cars. So we have to think about that. So any thoughts on where we go next?
I'm raising my electronic hand.
Yeah.
I'm going to jump in
Please.
there.
Go ahead.
And then I have to hop off for another meeting. But I would be very much in favor of the community FAQ and possibly a tutorial. I mean, I know that that could, as you say, infringe upon existing NCAR resources. But I know as I think it was either a late stage postdoc or early career faculty member, I attended the CESM tutorial. And I had already been using CESM, but there were so many things that I didn't know that I could do with it that I learned to do in the tutorial. But I knew it was very much geared towards how to do Earth simulations. And I was like the one exoplanet person in the tutorial saying, but how can we do this? How can we do that? So being able to have some kind of a dedicated tutorial or offshoot session at a workshop where we learn how to adapt CESM2 for these alternative Earth scenarios or exoplanet scenarios. I'd love that. And then maybe in the meantime, this community fact where you can see like what you can do, because it sounds like from what I see in the chat, there may not be always the necessity to go to something else like ExoCam or E2, you know, like that there's already some modifications in place beyond the ones that I may be using that I'd love to know about.
Betty?
So I'll just follow up on those comments. Maybe we could consider something like an ASP workshop in the summer where we bring in speakers, because I learned a lot here. There's a lot of climate dynamics, which is my background, and a lot of these applications. But you could add a tutorial in the middle. You bring in students, you bring in speakers, and I think it'd be exciting. Whether we need another working group yet, probably not. I've been involved co-chairing the Paleoclimate Working Group for years. I stepped down. Colin's talk was actually submitted to our working group this time, but I convinced him to speak today. And I kind of coined the word alternative Earths because it really, we are doing things even beyond what we've done in paleoclimate, going to with Wacom and Wacom X and exoplanets and thinking of chemistry. So there's so much exciting. So in some ways it's an extension, but not really, I think. But let's not do a working group quite yet unless COCON really wants it. But yeah, I like the idea of, because just some of the mods you showed them, I didn't know we could do some of that with CESM already. So, on that, NCAR.
Mm-hmm. I think first of all, we probably need to put together a mailing list to try and at least think about how we could. Yeah, I mean, it's probably not that hard to create an FAQ somewhere, and we'll have to look into that. But yeah, let's try and build a little bit on this momentum that I've seen today. I think it's amazing, so worst comes to worst, just we have a list of people that attended, but send me an email and I'll try and put an email list together. I know Eric had a list of people that he sort of solicited to attend this meeting, and we can build on that and maybe start putting together this FAQ and then and see where it goes from that.
And Colin just mentioned he has an AGU session on Earth system evolution.
Yeah, we're always happy to take deep paleoclimate model results in that session. We intend to always have it there.
Great. And there was a great amount of discussion. I hope that during this, and unfortunately we didn't have time to have that post talk, but I think hoping that triggers at least a few emails going back and forth and follow-ups. So Eddie, I think we're already 20 minutes over, so we should probably call it a day. And thanks everyone for their talks.
Yeah, it's been great. Thank you. I think at the maximum I saw 30 participants, maybe a few more. So a lot of interest in this topic.
We were up against that trendy AI ML thing, so I thought we did pretty well.
So thanks everyone, and have a good rest of the day, or maybe it's morning for some of you. So thank you.
Yeah. Bye-bye.